Okay, guys, how are you? I hope that if you are watching our videos, we are covering some of the concepts of aerospace and nautical engineering, especially at the beginner levels, and obviously getting our concepts right with the help of the numericals, with the help of the lab manuals, and also with the help of the other software material. But right now, what we are doing is a lab session, or we can say a lab test regarding the drag polar estimation using Cessna 206H at cruise mode. This is the title of the experiment that needs to be done at the laboratory level, so that we can check what are the results from this experiment, and hope we can understand well about the aircraft and aerodynamics. The aim is to estimate the drag polar using Cessna 206H at cruise mode. What is drag? What is polar? Let us see. Introduction. The drag polar is the relationship between the lift on an aircraft, and its drag, expressed in terms of the dependence of the lift coefficient on drag coefficient. So normally we have to deal with two coefficients, lift coefficient and a drag coefficient, and it is expressed in terms of L and D. So normally there's a lift, and obviously lift is upward, and the corresponding to lift, the weight is downward. When there is a drag towards the left side, the aircraft, there would be the thrust on the parallel but on the opposite direction. And we're just going to deal with the drag polar, which is the relationship between the lift on an aircraft, which is acting upwards, and drag, which is acting at a perpendicular direction to the lift. So obviously we have to consider the coefficient as well. Many performance parameters can be determined from drag polar, such as best climb, glide ratio, and optimum cruise, etc. These are the some of the other parameters, or you can say the properties, or the other aspects that we can get from these from this relationship. And CD is equal to CD plus KCL of square, and the one component KCL of square here is the induced drag of wing, which is the second part, and unavoidable component of wings lift. Obviously we cannot actually avoid this component. Other drag components, or the essential parts, are the parasitic and wave drag, and have both constant components totaling CD, which is normally the first part, CDO. So CDO plus KCL squared. KCL squared is the induced drag of wing, and CD naught is basically the total of what the parasitic and wave drag. So how are we going to deal, and how are we going to understand the introduction we have gone through about what is the drag polar, and obviously it is the estimation or the approximation we're going to apply on the aircraft, which is Cessna 206H and at cruise mode. So what is cruise mode now? The cruise is the level portion of aircraft where flight is most fuel efficient. Obviously cruise is also the most majority of the part of the journey, so that is we have to be more fuel efficient. Cruise phase consumes a majority of fuel. That is obviously the majority of the fuel has been consumed in this. And in the cruise mode, obviously the cruise phase is different from the cruise mode, but in the cruise mode the aircraft needs to be efficient in terms of fuel, so that it can cover a long journey, a more and more journey in kilometers, or what unit you can say. But more altitude leads to added fuel economy. Obviously, when we rise up an aircraft, there would be less fuel usage, and there would be economy of the fuel, and that adds to the savings. But for the operational and for the aircraft control reasons, it's necessary to stay at cleared flight level. Obviously, that is a necessity requirement, because obviously just to remain safe, the aircraft needs to be under the supervision, under the operational and operational control of the aircraft station. So let's see what we have. Turning cruise speed for long distance, typical cruising speed for long distance, and commercial passenger flights is 470 to 500 knots. Typical cruising speed for long distance. Commercial passenger flights is 470 to 500 knots. Commercial or passenger aircraft are usually designed for optimum performance at their cruise speed. Okay, typical cruising speed for long distance commercial passenger flights is this one, 475 to 500 knots. You have to keep that in mind. For long distance commercial is this one. Commercial or passenger aircraft are usually designed for optimum performance at their cruise. That's understandable. At their cruise speed, this is also optimum cruise altitude for a particular aircraft type and conditions, including payload, weight, center of gravity, air temperature, humidity, and speed. These are the another parameters, and at this altitude, which is normally the altitude at this altitude altitude drag is minimum and lift is maximum. Okay, so this is how you're going to, at this altitude drag is minimum and lift is maximum. And at cruise mode, aircraft in communications with air traffic control ATC station. So aircraft in communications with aircraft control ATC station. Obviously at cruise mode, what was done, aircraft is in communication with air traffic control station. That is obviously unnecessary. The aircraft needs to be in communication with the aircraft control station. Okay, so cruising speed for the long distance speed we have done is 470 to 500 knots. Commercial or passenger aircraft are usually designed for optimum performance at their cruise speed. This is also optimum cruise altitude for a particular aircraft type and conditions, including payload, weight, center of gravity, air temperature, humidity, and speed. Okay, so general tendency is to follow a straight line towards the destination. These may be some deviations from the flight plan for weather, turbulence, or air traffic reasons after receiving clearance from air traffic control. Okay, so Cessna 206H parameters are in front of you, parameter with the values. Normally I have discussed in the last video as well. I'm going to take out a practical example in terms of actually an aircraft parameters. The parameters are in front. Rated RPM, which is the revolution per minute for the engine, is 2700. RPM is manifold. It's manifold. It's a manifold pressure. Manifold pressure RPM is 29.97 in of mercury. Okay, sea level temperature, okay, which is this TS is 15 plus 273.15 Kelvin. Wing areas is 174 feet, 0.929 per meter square, and wingspan is this, which is H is 36 feet at 10.9728 meter. And rated HP is also 300 HP, which is 22370.96 watt. So unit conversion, 1 Celsius is equal to 273.15 Kelvin, 1 square feet is 0.092, 903 meters square, 1 feet is 0.30480, and in meters, and 1 horsepower, that is HP. Rated HP means rated horsepower is 300 horsepower, which is 2237099.96 watt. So 1 horsepower is 745.69 watt, that is standard. 1 knot is equal to 1.514 meter per second. That is the unit conversion, the standard unit conversion. The instrument used for this experiment or testing is 8-speed indicator, in which we have discussed in the last video. That is why I've taken this experiment for the purpose of further explanation. Engine, which is the RPM indicator, engine RPM indicator. Manifold pressure gauge, okay, which is we have discussed in the parameters RMP, and outside air temperature gauge, and altimeter, and sixth one is stopwatch. So these are the main instruments that we're going to use to complete this experiment or testing. Just for the drag polar of Cessna 206 H at cruise mode. So procedure would be airplane is made to cruise at different airspeed, understandable. During the cruise altitude outside, let's see, altitude outside the air temperature, and during the cruise altitude outside air temperature, engine RPM, these are the parameters, engine RPM, and manifold air pressure RMP, and time T is noted from instrument panel and from stopwatch. Obviously instrument panel is in front of you. These are the 5 instruments, and also stopwatch. So we have to check all these characteristics or properties against the instruments, so that we have to record it. The recorded data plotted to generate a linear curve, okay, zero lift drag CDO and induced drag coefficient can be calculated from intercept and slope of graph. That is understandable, intercept and slope of graph. We need to calculate from that one. So from this we get the recorded flight data table, okay, for which we have got CD naught, and also we have got the CD naught, and Oswald efficiency factor E, and induced drag coefficient can be calculated from intercept and slope of graph. Okay, so we have the graph, and then afterwards we can, from the graph we can calculate all these. Zero lift drag CDO, just in terms of intercept, and in terms of slope of graph we can calculate the values as per in the given equation, which was first one, CD is equal to CD naught plus KCL of square, having the components, two different combined combination of different components together. The table is in front of you. Outside atmospheric temperature OHT is equal to altitude, that is the outside atmospheric temperature, which is altitude. Okay, so V is in knots. Okay, we have to test some of 4 to 5 experiments. V is into knots, MP is manifold pressure, RPM revolution per minute for the engine, and BHP is what? Brake horsepower, and BHP when multiplied by velocity we get the other values as well. So just to plot the values, and we get the relationship in terms of slope and intercept, which is CD, and also with the drag coefficient as well. Okay, so this is how you're going to The brake horsepower equation is in front of you. Brake horsepower is drag force multiplied by velocity. That is the equation. The bhp is 1 rho v square of s, and that drag force would be multiplied by CD naught plus KCL, which we have initially determined, and multiplied by V. Just doing the mathematical portion and just doing it, we get this value: CD naught half rho V square SK, and it also with 2W, which is rho V square of S. So just cutting it out, we get this value, which is P brake horsepower velocity. That is the equation which we can use for our further at international standard atmosphere. That is also the condition which we normally can apply and use this equation and calculate the brake horsepower. Okay, and further tabulate it in this table, and we can calculate and further form a linear curve or linear graph. So this is how you're going to use the recorded flight data, okay, and plot it, and you're going to have the equation for the brake horsepower equation as well. The purpose is just to keep in mind that we can use different types of instruments to calculate the different parameters, and at the end we can help to actually get our required results. This is the main purpose of actually opting in for this video and recording it as a laboratory experiment, okay, under standard conditions. So this is how we're going to perform it. So outside atmospheric temperature is equal to altitude. So a brake horsepower equation is in front of you. You can actually calculate and use it. If you are interested in having the further explanation of international standard atmosphere, we can have the table as well. We can have the explanation in terms of graph as well, and also with the help of equations. If you are interested just to get the understanding of the national standard atmospheric relative to pressure, relative to density, and also relative to temperature, and also relative to altitude as well. So we can actually give you the graphical representation along with the equations and just the explanation of this equation further down the road, and obviously it may help us to get a clear understanding of international standard atmosphere used for understanding conditions as well. So this is how normally you can use this table when you have the recorded data. You can obviously, we don't have any equipment right now, but obviously if you are interested to apply this experiment in real time, you can get the real-time solutions and real-time results, and you can check against the different scenarios, different situations, different volts, and obviously you can have the results as well. So this is the purpose of opting in for this video. So what we have gone through, we have gone through the drag polar estimation using Cessna 206H at cruise mode. We have gone through the drag polar estimation, which is this one, okay, but obviously with the help of drag polar we get the best climb, which is, you can say, the altitude as well in terms of, and we can have the glide ratio, we have the optimum cruise, etc. On optimum cruise we have discussed the optimum performance at which we get the optimum performance, and optimum performance, this is also called optimum cruise. We have the optimum cruise, for example, we have the optimum cruise altitude, we have the optimum performance, and these are the just the optimum cruise parameters such as altitude for a typical particular aircraft, type and conditions, and we need to understand the type, which is normally this is 206, Cessna 206. We have some, if you have some other type of aircraft with the particular conditions, obviously the optimum performance would be different, such as the cruise altitude and speed would be different. So you need to understand the temperature, you need to understand the humidity, the speed, the height, the center of gravity. So obviously the drag at this altitude, which is the optimum cruise altitude, drag is minimum and lift is maximum. That is the relationship of drag polar as well. So at the optimum altitude, we have the drag is minimum and lift is maximum. But at cruise mode, obviously aircraft needs to be in communication with the aircraft control ATC station. So this needs to be understood, so that at the optimal altitude, drag is minimum and lift is maximum. So with the parameters given, different parameters with RPM and manifold pressure, sea level temperature, wing area, wingspan, and rated horsepower, we can have converting it into standard form, using it against the instrument, and calculating under the standard conditions, and obviously at the given parameters, such as the just calculating all the stuff and recording it and plotting it, just to see that where it is the slope or intercept, to get the the lift and the drag results, or lift and drag coefficients, just to complete the equations, and we can see what are the different results for different parameters. So this is a short type of video, not actually directly linked to the airspeed indicator, but obviously the instruments are used, but that is why I have actually used it. You can airspeed, the true airspeed, which we actually discussed earlier, was actually related to the aircraft, and to some sense drag and airlift, which is the part of the aircraft, is not directly related, but you can say that because the reason of the use of the instrument, I have actually taken this lab experiment. But further, if you are interested in explanation of any other concepts related in this lab experiment, we can have another extra video, or you can share some thoughts in the experiment in the comment section. We can follow on those lines and help us complete the concepts. So I'm going to end up the video, and hope to see you with some other interesting facts and other interesting concept. And till then, I hope that if you are watching our videos, and if you are not, if you have just recently joined our channel, then you can actually comment, like, subscribe, and we can actually improve on those lines as well. To hope to see you soon with some other interesting concept. Till then, thank you, take care, and have a nice day.